This is a short video about linear systems, so the general n by n case. So we're going to generalize what we did with the 2 by 2 case. So the setup for this is instead of having two functions, say x and y, like we're used to playing with, say I've got n functions, x1, x2, all the way up to xn, where t is the independent variable through all this. And what's convenient for us is to talk about all these things at once, I'm going to call that just the vector x. So x is the vector whose components are these functions x1, x2, and so on. So then x prime would be the vector whose components are the derivatives of those. Now, what are we tasked with doing? Maybe we've got some system of differential equations that look like, well, x1 prime is equal to some linear combination of x1 through xn. So these a's, that's like a double subscript, so like a11. So it's supposed to represent, you'll see in a moment too, it's the coefficient on x1 in the first equation is what the subscripts are, again, supposed to represent. So what's the point? We're going to try to, instead of writing this system of equations in this more college algebra kind of way, what we're going to try to do is, like we did last time, write it in this more linear algebra kind of way. And so we'll pull it apart the exact same way. We'll call this vector here, like we said above, that's x prime. What we'll do is we'll call the orange coefficients, we'll call that matrix A, and that would be that matrix A multiplied by this vector x here. So down here, the big star that you've probably been looking at for like a minute is what your system of differential equations looks like in matrix notation. And something that's kind of striking about that, right, is, that's kind of a simple looking equation, but you see that it encompasses a whole lot of information. So the next thing you want to talk about is, how do we solve that stuff? And to set it up, what we need to be able to do is we need to be able to find the eigenvalues of this matrix A, of this coefficient matrix, just like we did before. So maybe to remind you, the eigenvalues are the solutions to this polynomial equation, determinant of a minus lambda I equals 0. So a little bit more detail here. The determinant of a minus lambda I, it's very hard to take a determinant of a large matrix. So like 2 by 2s are easy, 3 by 3s are still doable, 4 by 4s are a pain, and then some of these are just, not worth time to do. And that's where computers come into play, and that's kind of a whole field of study called like numerical linear algebra. It's whenever I want to extend some of these techniques that I know I can do by hand, but I'm just not good enough to do them, maybe that many at a time. So computing this determinant itself can be very hard if your matrix is hard. Nonetheless, though, like all the theory and all of the steps that we're going to do, they're really going to follow the exact same stuff we did for the 2 by 2 case. So anyway, that determinant, a minus lambda I, hard to compute maybe, but it's still a polynomial, and it's of degree n, just because the size of your matrix is n. Now, what else can we say from that? Well, if you've got a polynomial of degree n, you know that it's got n solutions if you're allowed to include complex numbers. And that was the fundamental theorem of algebra, due to Gauss, who proved a whole lot of stuff in math, one of the most famous mathematicians of all time. So A has n eigenvalues. So like remember, when you had a 2 by 2 matrix, it had two eigenvalues. Maybe they were two distinct real numbers, maybe it was one repeated real number, or maybe it was two complex numbers. I'm saying the same kind of stuff works here. If you've got n eigenvalues, maybe some of those are distinct real numbers. Maybe if you've got 20 eigenvalues, maybe 7 happens 4 times, maybe it repeats. But then also complex eigenvalues still have to come in conjugate pairs. So like if 1 plus I is an eigenvalue, so is 1 minus I. So from before, or maybe just to remind you too, some more basic linear algebra kind of stuff. If lambda is an eigenvalue with eigenvector v, like what could you write down? That means that that matrix A times v should be the same thing as just lambda times v. All right, so again, what we're trying to do is we're trying to pick out, are there any vectors v that this matrix A basically just rescales, just stretches or shrinks or changes the direction, right? So hope it makes sense kind of geometrically what this kind of eigenvalue equation is saying to you. Now, how do we find solutions to this system of equations, this matrix equation here? So what we'll try to do is, like we did before, maybe I'll guess that this function, or this kind of vector of functions, e to the lambda t times v, where lambda and v are eigenvectors, an eigenvalue with eigenvector v of a. So what we're going to do is we're going to plug that into our matrix equation here, and I tried to color code this stuff so you can kind of see what's going on. So let's see. X is really this exponential here, so I'm going to plug it in here, and I got to take the derivative, and then I plug that in here as well. When you take the derivative, remember t is the variable, so like how do you differentiate that exponential? Well, the lambda comes down, and v is just a constant vector, so it just sticks around. So when you do that derivative on the left, again, just a lambda comes down. And on the right, what I'm trying to remind you of is think about that eigenvector-eigenvalue relationship up here that I've highlighted. AV is the same thing as lambda v, and I'm trying to say here, hey, you've got an AV right there, therefore you can rename it lambda v. Now why did I do that? It's because I'm trying to show you that when you plug in e to the lambda t times v, you end up getting the same thing on both sides. In other words, you verified that that makes the equation true. And again, that's what it means to be a solution to the equation. So what do we got? Any multiple of e to the lambda t times v is going to solve that system of differential equations whenever lambda and v are eigenvalues and eigenvectors of a, respectively. And so for that, when you're actually doing some of these by hand, some concrete examples, the same tricks that you had before are going to apply. So in particular, like, if you get a complex eigenvalue, maybe you're going to need Euler's formula to break it up into, cosine stuff plus I sine of stuff. And maybe you're going to have to solve an extra system of equations whenever you run into repeated eigenvalues. That stuff can still happen for this more general case. But nonetheless, I hope that you kind of see the theory and the method in order to get the solutions. It still kind of works the same way, which is nice. And that's kind of the point of taking some of these math concepts and kind of defining them in this abstract way. It's so that there's nothing special about 2 by 2. We could do the same kind of stuff for a 100 by 100 type of project.